Hello everyone, welcome to Pepcoding. So in this video, we are going to start another interesting question. The name of the question is pre-order merge traversal and a binary tree. So we have already discussed in-order merge traversal. So in this video, we are going to discuss pre-order merge traversal. Okay. And but before that, I want to tell you that if you have not watched the video of in-order merge traversal, then for that, kindly go and watch that video and then continue with this video, because with this way you will get a better insight of this question. Okay, because the main points will are already told in order video. Okay, so go and watch that and then continue with it. So let us discuss the question. So in this question we'll be given a binary tree. Okay, it is a binary tree and we have to traverse the pre-order of it. Okay, we have to print the pre-order of it, and for that we are not going to use recursion, we are going to use Morris traversal. Okay, we are going to use Morris traversal. So why Morris traversal? Because Morris traversal takes O1 of space, recursion takes O(n) of space. Okay, recursion takes O(n) of time, it also takes O(n) of time. So as the both time complexities are same, but the space complexity is different for both of them. So this is why we are looking into this Morris, because it has a better space complexity. Okay, so let us look into this Morris traversal, that how we are going to traverse into it. But before that, let us see how was our recursive solution. So in recursion we used to do print a node, go to its left, go to its right. Okay, a call for left, a call for right, and in this way we used to print the pre-order. Right here we used to print the pre-order. So what happens, see, this is my Euler path. I start from 2. What I'll do, I'll print 2, I'll make its left call, go to its left, again I'll print 7, I'll again go to its left, so it will say go to 2 and print 2. Now 2 will say go to my left, so nothing will come from the left, nothing will come from the right. It will again reach to 7 and will reach to 6, so 6 will say print me and go to my left, so it will go to its left. So 5 will give nothing, but 5 will print itself, will make it both of its call, and then we'll go to 6. 6 will now execute its right call, so it will print 11 from that and it will go back to 2. Then from here it will come to 5 and will print 5. Okay, and then it will reach 9, will print 9 and go to the left of the 9, and 4 will print itself first, then make its left call, then right call. It will get nothing from it and it will go to 9, and in this way the whole stack will be empty. Okay, so this is my in order traversal: 2 7 2, and then 6 5 11, 6 5 11, and then 5 9 4 5 9 4. So this is my pre-order traversal. So this is how we are going to traverse in recursion, but recursion was using stack space. Let me show you the stack frame that it was using. So it was like we know that, right, that print then left then right, we know that call and the printing statement, so not gonna write that again, but let me take this stack. So this will be my stack. Okay, this is my stack. I'm going to use this stack. So how I'll work in it is, see, first of all we'll go to 2. Okay, here I'll write my pre-order, so I'll print 2. Okay, 2 will be printed, 2 will say go to my left, so left of 2. So now 7 will print itself and will say go to my left, 7 left. Now we'll reach to 2, print 2, left of 2. Left of 2 will give nothing, it will say go to my right. Right will also give nothing, it will come back to 7, and this will go out of this stack. Okay, so when I'll reach 7, then 7 will say go to my right, 7 right. Okay, so 7 right. From here we'll reach 6, from here we'll reach 6, so 6 will print itself, it will say go to my left, so 6 will go to its left. Here we'll see 5 will print 5 and 5 will say go to my left, will give nothing from the left, go to my right, will give nothing from the right, take it out of the stack. So now it will again reach to 6 left, right? From 6 left, it will make the call of 6 right. So 6 right here. Now we'll reach 11. So 11 will print, and then 11 left will give nothing, then 11 right. 11 right will also give nothing. So it will come out of the stack. Okay, so it will now reach to 6. Now after reaching 6, it will see that both of the calls for 6 are done. So it will also come out of the stack. Then it will reach 7. So it will again see that both of the call for 7 are done. Now it will reach 2. So both the calls for 7 are done. Now this. Okay. Now 2 left is done. Now 2 right will take place. So here we'll do 2 right. So now we'll reach 5. So 5 will print itself, and 5 left will call itself. We will get nothing from the 5 left. We'll do 5 right. Okay. So now 5 right will reach to 9 left. But 9 will print itself, then it will go to 9 left. 9 left will reach to 4. And 4 will print itself, make its left call. We'll get nothing, we'll make right call. We'll get nothing from that. Then we'll reach to 9 left. So 9 will make its right call. We'll get nothing from that. So it will come out of the stack. 9 left was also done. Then it will reach to 5. 5 is done with both of its call. Then it will reach to 2 is also done with both of its call. So this is how the stack will be emptied. Okay. So as we have seen that in recursion we are using the stack space, right? And almost at least once we are filling an item, okay, and then after filling we'll printing it, okay, like it is processing, right? The same way that I have shown you here. So in this way, almost on of space we are using, okay, almost on of space we are using, but this space can be minimized using this Morris traversal, okay, because here we are not going to use recursion. We are not going to use recursion and any other extra space, okay, and not any other external stack or anything. We are going to traverse this binary tree, okay. So how? Let us see. So for this, as I have already told you in the video of in order traversal, we are going to use the concept of threaded binary tree. So in recursion we have seen that from here I can come to this node, right? I can come to this node because it erases itself from the stack when it will be done it with both of its calls, okay. So it will come here, and then from here I can also come here when it will be done. Then 5 will be done with both of its call, okay. And from 6 also I can go back to 7 because it will be done, 6 will be done with both of its call, and then it will come to 7, and then I can also come to 2, okay. So in this way I can traverse my tree in the pre-order as I have in any order with the help of recursion. But how I can do this without recursion? Because no stack will be allowed, okay, no pushing, no popping will be allowed. So how we can do this? See, for this, the threaded binary tree concept says you can go to this node to this, right? You can go from this to this. You can also go from this to this because you have link, right? But from here you cannot come back to this. Why you cannot come back to this? Because coming back to 7, you need a link. You need a link which a child cannot have. Child cannot have a link to its parent in a binary tree. In a binary tree, a child cannot access its parent, okay. So this is what we know. But what this Morris is saying that, okay, you cannot go back, but you can make a link. And let us call this link a thread, okay. Let us call a link a thread. So you want to go to 2 to 7, right? So for that I'll help you in making a thread. Somehow you will make a thread, and then you can go back, right? Yes, you can go back now. So this is thread concept, okay. Now from this I reach to this 7, right? Now what I want to go 6. I can easily go 6 because here is a link. I want to go 5. I can easily go to 5. I have a link. From here I need to go 6. So what I'll do, I'll make an this. This is also again a thread. Okay, so again I'll make a thread from this to this. Okay, from this to this I made a thread. From here I'll not make a thread because from here I don't need to go anywhere, but from here I need to go this end. So this is how my threads will be made in this binary tree. Okay, and with the help of these threads I'm going to traverse the whole tree. Okay, so let us see how we can achieve it. I hope that it is clear. This threaded binary tree is clear. I already have told this in previous video also, but still we are discussing it here. Okay, now, so what happens in my Morris traversal? We'll discuss that again. So I keep a pointer here, current pointer here, and a left node here, right? So we'll write this mark to discuss our time complexity again. Okay, that how many times a node is visited. So first node is here. Okay, and then I put a left node to the left of it. Okay, so let us see the conditions. Let us see the conditions of traversing. So from the starting, I'll start from the root node, right? And I'll go to left. I'll go to my left. So every time I'll go to my left. But when I will go to my right, someday I'll go to my right, right? But when will I go to my right? So the conditions for going right traversal. That means when I will go to right side, or we can say right side traversal. So when left tree is completed or no left calls remaining. What I mean is, see, if you are at this point, then you want to go to this, right? If you are at this point, then you want to go to this. So what this means is, this means that when this left side is ended, you have to go to right. That's right. Yeah, it is saying the same thing that we used to do in recursion. When the left side is completed, you have to go right. Okay, we got the point. And when left side is fully processed, see, from here also you go to right, right? So when you go to the here, we have not seen that my left tree is being empty. I mean, there is no left side. The here is left side is remaining, right? But from here I have to go here. How I can go? I will see that my left tree, this subtree, my left subtree is processed. If left subtree is processed, then again I'll go to my right. Okay, so these are some conditions in which I'll go to my right, and otherwise I'll keep on moving to my left side. Okay. So I hope that these points are clear. Okay, and we will see the conditions for printing also, that when we are going to print. So here is my C, here is my left node. So what I used to do, I used to find the rightmost node of this left node. So here is the rightmost node, and I used to check if the right of rightmost means right of rightmost this time is null. So I'll check if it is null or not. So if it is null, then it means if rightmost is null, right of rightmost is null, then that means need to create thread. That means here I need to make thread, so I'll create a thread. Okay, right is null, so it means that I'll create a thread here. Okay, so after creating thread, I'll print this too. Okay, I'll print this too. One more thing that you need to observe, that for every node that is having a left node. Okay, this node have a left node, this node have a left node, this node does not have a left node, this node have a left node, this node does not have a left node. So every node that has a left node will be connected. Okay, have a connection. So all the connections, see, this has a connection, this has a connection, so this will come in my pre-order, this will come in my pre-order, This will also come in my pre-order, but this will also come in my pre-order, but it does not have my left node. See, you have to observe, it does not have my left node, but it should come in my pre-order. It does not have a left node, but it should come in my pre-order. It does not have a left node, it should come in my pre-order. It will not come in my pre-order, it will go like this. In this way it will come to my pre-order. It will already come to my pre-order because I know that the one which has connection, it has connection, it will come. It has connection, it will come. It does not have connection, but it does not have a left node, so it will also come. It has a connection, it will come. And then it does not have a connection, or also it does not have a left node. So this is how I'll take it into my order, pre-order. Okay, so see, what I have written here is, when my right of rightmost is null, then I need to create a link. Okay, I will create a link. And the second thing is, I'll shift it to my right, I mean to my left. Okay, so here one time it is visited, second time it is visited. Okay, so I have I've sent it to my left. Now same thing, left node put here, make a connection. Okay, rightmost, find the rightmost is this only, 2 only. So check if the right of rightmost is null. Right of rightmost was null here, right? So make a connection. So we will make a connection. We made a connection. Now shift it to the left. Now this is an interesting case. This is an interesting case here. It is visited 2 times. Okay, one for the left node and one for this current node. So current node will come here now. So what will happen is, now when I create my left node, then it will be null. Left node will be null. So when left node will be null, at this point I am creating a connection. I'll print it. At this point I am creating a connection. I need to print it. I will print it. At this point I am not creating any connections, but here I can see that this person does not have any left node. So if my left node is null, then also I need to add it. So what I will do, I added 2, I added 7, I'll also add 2 again. Okay, I'll add this 2 and then we'll go back. Now as the left side is ended, right here it is showing that the left side has been ended. It does not have anything in the left, so shift it to the right. When it will be shifted to its right, then it will be like this. Okay, so when it will come here, what it will do is, it will again make a left node here, but this time it will find its, when it will find its right of rightmost, when the right of rightmost from here is not null, it is equals to current. So that means it is the point. We know that this is a mark. I already told you in the video of in order that it is the mark. When we get the right of rightmost is equals to what? Is equals to current. Then that means at this point I have already processed this side. So when I have already processed this side, then that time I need to go to my right. Also I need to end this connection, because if I'll not end this, my tree will make some cycle, which I don't want. Okay, so as I'll keep this left node here, so it will be visited once again now, and now it will come to my right. Okay, so C will come here. Now C is here, put a left node here, make a connection. Okay, made a connection. Now what will happen is, from this what will happen, it will go to the left. So from here C will come to this, so it will see. Okay, adding again. So it made a connection, add 6. Now C will come here. It has seen that it does not have any left node. So when it does not have any left node, add 5 and simply shift it to the right. The right of the 5 is 6. So it will be shifted here. Now my ln will come here. Okay, my left node will come here, and it will check if the rightmost of right is current now. So when it is equals to current, then what we used to do is, we used to go to right by ending this connection. go to its right by ending this connection. Okay, so now what I have seen is I'll put a left node here, right? I'll put a left node here, and after putting a left node, what I will do, I'll see that my left node is null. So when left node is null, add 11. Added 11. Okay, I added 11, and then what I will do, I will go to my right. So its right is here. So C will come here, and it will be like this. Okay, now again create a left node here. Find the rightmost. Now the right of rightmost is not null, it is equals to some current. It is equals to current. So when right of rightmost is equals to current, then at that point what you need to do is, see, right of rightmost is equals to current. So what we used to do, we used to shift it to right side by ending this connection, as this connection is made by me. So end this connection, shift it to the right. Okay, and see, it will be visited once again to find ln. Okay, it will be visited once again to find ln, and will reach here. So when it will reach here, what it will do is, see, it will make its find its left node is null, so again it will add itself and go to its right. So when it will go to its right, what it will do, it will come here, so when it will come here, it will place a left node here and then will make a connection. So after making a connection, what it will do, it will shift it to the left. So current is here now. So when current is here, it will see the left node is equals to null. So when left node is null, okay, here we made a connection, and so we need to add it. And again, here at this point, when left node is null, I need to add it. So I will add it, and then I'll go to my right. Okay, because left node is null means left side is empty, there is nothing in the left side, go to right. So when I'll go to right, I'll reach here. So after reaching here, what I'll do, I'll put a left node here. Okay, I'll put a left node here, and then we'll see what is the right of rightmost. Right of rightmost is equals to current. So when right of rightmost is equals to current, then at that point, what you used to do, destroy the connection. So destroy the connection and shift it to the right. So when it will be shifted to the right, then it will go to null. At this point, you need to stop. And this is the pre-order that you want. So where we have printed it, let us see where we have printed it. At the point, see, at the point when left node is null, at that point print, right? At that point, here when left nodes were null, we were printing at that. And other thing is, when my right of rightmost, see, when my I'm creating a link. When I was creating a link, that means right of rightmost is not equals to, is equals to null. I was creating the links when it is null, right? So when it is equals to null, then print. In these two conditions, I need to print this and this. Okay, so we will remember it. We have seen the dry run. Just write it into the code. So let us try to write the code for the same thing. Okay, again, one more thing. See the number of time it is visited. Number of time it has been visited is at least 3. Okay, might be some marks are missing, like some marks maybe are missing. Okay, because sometimes it happens that when we are dry running it, we don't remember exactly how many times we need to write this cross. Okay, so it happens sometimes, so maybe the number of crosses are come, but we have seen mostly we have 3 or 4 crosses, right? This is 1, so at least 1 will be visited everyone. This is visited 3rd time, 3 times, this is 3 times, this is 4 times, this is 3 times. So almost all are visiting 2 to 4 times, we can say. Okay, so average we can say 3 times. So if I'll talk precisely, the time complexity will be not in terms of O. The time complexity precisely will be O of 3n. Again, in the On terms will be big O of n. Okay, in On, if I talk in big O, then it will be On, but in precise, it can, we can say it is 3n. Okay, sometime it goes to 2.7 or 2.8, but to be precise, or if in the whole number term, then we can say 3n will be the right digit. Okay, 3 1 will be the right term. So this is the time complexity. Okay, you can do it by your own, this dry run, you can do this dry run by your own, and I want you to put these crosses so that you can get to know that how many times a node is visited. Okay, so you will get an idea from there. So let us go to the board and try to write the code. Okay, so we'll write in Java. Okay, so let us write the code. Where is that? Yeah, here we need to complete this function. Okay, so what we need to do, let us make first of all our currents. Okay, so tree node current is equals to root, right? We used to put a current node into our root, and we need to return an array list, so let us make that also. So array list of integer, array list of integer, answer is equals to new array list. Okay, so this is what we have, and then after that, what we will do, we will do some work while current is not equals to null, right? Till then we will do while current is not equals to null, till then we will do some work. And then first of all, what we used to do, see, let me show you here only. What I was doing is, my current is here, and my next node, that means my left node, this, my left node is in the left. So let us make a left node, because on the basis of left node we are taking some decisions, so we need a left node. So tree node left node is equals to current dot left, right? So it is my left node. Now what I'll do with it, I'll check if my left node is equals to null or not. If it is, then we will do something, else we will do something. So when it is null, then what that means, is it null at this point, where I am? See, my current is here, so my left node will be here, right? My left node will be here. Is it null? No. Here, if I'll see, if I'll reach my, if I'll take my current here, then at this point my left node is null, right? So what I'll do is, suppose from here I make a connection, I'll print it from here. I'll make a connection, I'll print it from here. I'm not making a connection, but I need to print it because it should come in my pre-order. Like this will come in my pre-order, this will come in my pre-order, and this will also come in my pre-order. So how I can add it? I can add it when, by saying that this is the last element. Okay, because we have already discussed this in pre-order also, that this is the last element, so it should be added. So that means my answer dot add current dot value. Okay, so this will be added, and what I used to do, I'll say that my left end is finished, my left tree is being finished now. Okay, there is no call remaining in the left. Okay, there is a difference between processed and finished, so it is finished right now. Okay, so when it is finished, I need to go to the right side. So what I'll do is, I'll shift my current to my right. Okay, this will be done, current will go to its right. Okay, so yeah, so current will go to its right. And in else condition, what I used to do, see, this is my tree, Okay, so this is my current, this is my left node. So I am finding the rightmost, then making connection. I'm finding the rightmost and then checking its right of rightmost. Okay, so let us make a rightmost node. So tree node of rightmost node is equals to what it will be. It will be let us make get rightmost node, and I'll pass left node and current into it. Okay, why we are sending these two we have already discussed in our in order video, so not going to discuss this again. Okay, and while not while if I used to check after finding this, what I used to check in rightmost node. See, tree rightmost node. This I'll write this function after some time, and but till then let us believe that this will give me the rightmost node. Okay, so now I have the rightmost node. So what I'll check is if right of rightmost node, rightmost node dot right is equals to null or not. If it is equals to null, do something else, do something. If it is null, then it means that it does not have any connections right now. So I should make the connections. I should make some connections here. So make connections and add to pre-order. At this point, we were adding at pre-order, right? When we were making connections, we were adding it to pre-order. So this is what we have to remember. Okay. So this is how it will be. And what we'll do, we'll make connections. So for making connections, what I'll do, rightmost node dot right is equals to what I should put in the right current, right? In the right of rightmost, I should put this current. So this will make my connection to my current. Okay, so now connection is being made, and after making connection, what I will do, RIGHT rightmost node dot right is equals to current. Okay, connection is being made, and I need to shift it to the left also, and also need to add it. So now answer dot add current dot val is shifted to the left now. Now current is equals to current dot left. Okay, so this is done now, this is done now. And what else we need to do? We need to destroy the connections when it is been available. Destroy the connection. So this is the line where I'll destroy the connection. So what I'll do, if I find some connection, see this see, look into this tree. So if the connection is available, then what I'll do is I'll simply remove this connection, but I'll point it to the null, it will be removed. But also I'll shift it to my right, because this left subtree at this time will be processed. Okay, this left subtree will be processed, so shift it to the right and then destroy the connection. Okay, so no issues. So what I should do, I should my rightmost node dot right is equals to null, it is equals to null. And then my second thing will be my current will go to right, current is equals to current dot right. So this will be done, and I should return answer from here. Okay, as it need error list in return. So here let us give it a look. So current, when current is not equal to null, make a left node and then check if the left node is null or not. If it is null, then add that value and go to its right as the left end is finished. Okay, and otherwise what you should do, you should make a rightmost node. Okay, and okay, rightmost node, get rightmost node is remaining. So public static, it will give me tree node, right? So tree node get rightmost node and pass it the left node and current. Left node comma tree node current, tree node left node, and tree node current. Okay, so what I'll do, I need to find the rightmost, right? So what I'll do, rightmost of left node. So left node dot right is not equals to null, right? And left node dot right is not equals to current. So in these two cases, I'm in the safe place. So shift it to its right. So left node is equals to left node dot right. So it has been shifted now, and at some point it will reach to its rightmost place. So return left node from there. Okay, so left node will be returned, and anything else. Yeah, that is all. I think it is, we are done with the code. So let us try to give it a submit. Okay, so it is accepted in the first run. Let us give it a final submit for all the test cases. Okay, so it is completely accepted. So I hope that you got this video. Okay, it was completely linked with the last video, that is my uh in order traversal. Okay, Morris in order traversal, and we have already discussed the time complexity. Okay, time complexity is O(n), and in precise it is 3n. Okay, and space complexity is O(1). It is such a cool technique in which we can solve, and we can traverse a binary tree in O(1) space complexity. Okay, that is why it is cool. So after this, we'll meet in the next video. That's all for this video. So don't forget to like the video and subscribe the channel and share it with your friends. And until then, goodbye, take care.